Hi everyone, my name is Celina and I am a member of the 2023 Knauss Lunch and Learn Committee, and on behalf of the committee I'm pleased to introduce Hannah Lohman. Hannah is an environmental engineer working to advance global sustainability efforts related to water and sanitation infrastructure, renewable energy, and natural resources. Hannah is a 2023 Knauss Fellow working with the NOAA Climate Program Office Climate Adaptation Partnerships Program, formerly known as RISA. As the Climate Adaptation Science Policy Fellow, she works to support the coordination of regionally focused community research priorities on impacts and adaptation science across the CAP network and with relevant partners. Hannah recently earned her PhD in environmental engineering in May 2023 from the University of Illinois Urbana-Champaign, where her research focused on developing decision-making tools to evaluate the sustainability trade-offs of water, wastewater, and resource recovery infrastructure alternatives in resource-limited communities. She also has an MS in environmental engineering and a BS in civil engineering with an emphasis on environmental hydrology and hydraulic engineering. Throughout her undergraduate and graduate careers, Hannah has had the opportunity to work on international projects focused on improving access to drinking water and wastewater treatment for communities in Honduras, Rwanda, and Uganda, and innovating agricultural technologies for subsistence farmers in India. Outside of her work, Hannah enjoys spending time with her family. She's the third of 6, hiking and exploring nature with her mini Australian Shepherd, Lulu, taking care of her houseplants and trying new hobbies. Her current one is cross-stitching. So take it away, Hannah.
Thank you. So today I will be kind of switching gears and talking more about my PhD research, and specifically on the topic of characterizing sustainability of wastewater and resource recovery infrastructure for an informal settlement in Kampala, Uganda. Okay, so Bwaise is the informal settlement in Kampala, Uganda that I had the opportunity to work in at the end of my master's and throughout my PhD. And specifically, they are seeking to improve and increase access to their sanitation services, which is another word for their wastewater treatment. Specifically, Kampala is the capital of Uganda, and then Bwaise is located in the northwest region of the city. And I also wanted to recognize everyone that has played a role in this research. And so we did a field visit in 2018 to the community and worked extensively with partners there. And we worked with the Moderator University and had partners with their students to do community surveys. And then we also worked with a community-based organization called Community Integrated Development Initiatives. And they do a lot of work in the community related to water and wastewater, as well as other community needs. And so specifically, when thinking about sanitation, we are targeting achieving universal sanitation coverage by 2030, which is the Sustainable Development Goal Target 6. And currently the rates would need to be quadrupled to meet that target, especially in the vulnerable populations. And so when looking at Uganda, 8 out of 10 people still lack access to at least basic sanitation services as of 2020. And basic sanitation is really any facility that separates human waste from human contact, and they're not shared with other households. And so an example of basic sanitation would be a pit latrine with a concrete slab. And this picture shows what that would look like. And so in Uganda, only 2 people have access to this type of sanitation system, whereas 8 people would have access to something with lower quality than this. And so even when we're implementing sanitation systems in these contexts, about 70% of the systems fail within the first 2 years. And so these failures stem from a lot of different things. Specifically, there's not a lot of funding around meeting these national WASH targets. 80% of countries are reporting that they don't have the funds to meet the targets. People are implementing one-size-fits-all solutions, so they're not really taking into account the local context. They're excluding relevant decision makers, maybe not really considering operation and maintenance considerations after the first year. And then there's also a lot of lack of transparency in how these decisions are made. And so the decision-making side is something that I was really interested in looking into for my PhD research, and that is what I'll be discussing today. And so as an engineer, we do a lot of modeling, and so I was interested in developing a tool that would allow communities to evaluate lots of different trade-offs for their sanitation and resource recovery, which is basically a sanitation system that you can recover resources from, which I'll discuss later. And so I, as well as other postdocs and graduate students, worked on developing this tool called DMSAN, which is a Python package for developing or assessing the trade-offs for sanitation and resource recovery systems. And so what is multi-criteria decision analysis? So this is a technique that can be used to evaluate multiple conflicting criteria in decision making. And so this is a common technique for engineering projects, but you can also use this technique for really any decision you have in life where you're thinking about different criteria. So it could be like thinking about what phone you want to buy, or what city you want to live in, or what job you want to take after your fellowship. And so the process of using MCDA is to think about what alternatives you're choosing between. So that could be the different phones you're choosing between. And then you'll think about what decision-making indicators you would like to use to assess each alternative. And so that can be, if we're using the phone example, that could be the cost of the phone, the camera quality, the looks of the phone, anything that matters to you for the decision. And then you can assign the weights, which is basically how you value each indicator. And so you could say costs are 60% of your decision, the camera quality could be 40%, and then maybe the looks of the phone is 10%. And then you would score each alternative based on their indicators. And so that could be lining up what the costs are for each of the phones, maybe the pixel quality for the camera, and then just more of a qualitative score for how well you think the phone looks. And then you'll take all of that information and do a lot of math to calculate one single score to determine what is the best alternative. And so this is kind of similar to a decision matrix technique too. And so for the sanitation specific multi-criteria decision analysis, we conducted a thorough literature review to look at what indicators are typically used when thinking about choosing a sanitation system. And then based on that literature review, we divided them out into different categories, which we're calling criteria. And so those are we had 5 main criteria, which were technical, resource recovery, which is the ability of the system to recover usable resources from waste like water, nitrogen, phosphorus, and potassium for fertilizer use, energy, you can recover energy from wastewater. And then we also looked at the economics or the cost of the system, the environmental impact, and then we had social indicators related to the actual use and acceptability of the system. And so some examples of technical indicators were the resiliency of the treatment, any operation and maintenance skills required, its flexibility to power outages, drought. I already gave a lot of examples for the resource recovery. The environmental indicators were damage to the ecosystems, human health, and resources in the community. And then some social indicators were related to the community surveys we did back in 2018 and were related to jobs created in the communities, the disposal of the actual waste, cleaning requirements, privacy, odor, things that are more related to the use of the system. And so the package is pretty flexible with how you can assign the weights of the systems. And so we have a 2-part weighting system. One is for those 5 criteria weights, so the technical, social, environmental, resource recovery, and economic. And then we also have subweights for each individual indicator for those 28 indicators. And so the indicators, those values and preferences can be defined by going into the community and surveying and asking them to tell you which indicator do you care more about, the costs or the environmental impacts. And then we also developed a country database, which was very helpful because this project was happening after that 2018 field trip, and it also was coinciding with COVID. And so we were unable to actually go back into the community to ask how they valued all of these indicators. And so we developed a country database to be able to understand kind of the general values for the country of Uganda. And then for the criterion weights, you could again go into the community and ask them to tell you which of the 5 they care most about. But since, again, it was COVID and we couldn't go and ask these questions, we developed a system where you can just look at the entire spectrum. So you can set the weight of the environmental to be 0, resource recovery maybe is 100%, and look at basically every single possible set of weights for those 5 criteria. And then, so for the indicator scores, some of them are quantitative, and you can model the sanitation system and calculate how much water is recovered for the system or how much energy you can recover, what's the cost as far as like the materials and construction of the system, what's the environmental impact. So all of those are quantitative and can be simulated in this other package, Python package that I'm not going to talk about today, but I put it there if you're interested in looking into it more. And then we also have qualitative indicators that can be defined by these predefined score ranges that we established. And so as an example of one of those indicators for the resiliency of the treatment type, you can assign based on your technology, if it's very low resilience, a score of 1, and then if it's very high resilience, a score of 5. And then when you're combining all of those weights and all of those scores, you can use a lot of different MCDA methodologies that are all based in mathematics. And so for ours, we did this TOPSIS methodology, which I'm not going to go into the details, but basically it just combines all of the scores and weights, and then we'll give you a single score output. And so this methodology was very common in the wastewater and water sectors. And so now I'll talk about how we applied this tool that we developed to the community in Kampala, Uganda. And so we evaluated 3 different treatment alternatives, and each alternative includes the same types of steps. So the first step is the user interface and storage, which would be the toilet system for the communities. And then conveyance is just taking the waste from those toilets to the centralized treatment plant. And then the centralized treatment is where we're actually treating the wastewater. And then recovery and reuse would capture any kind of water, energy, or nutrients recovered from the system. And so the first alternative that we looked at, I have some photos here from the community just for your reference, but this is the existing system in the community. And so this would be no upgrades to what is currently happening. And so a lot of the households are using pit latrines, which I was talking about earlier, and then would use a truck to empty those pit latrines and transport the contents of those latrines into the treatment plant. And then the treatment plant uses pretty conventional wastewater treatment using sedimentation, wastewater lagoons, which this picture shows what a wastewater lagoon looks like, and then drying beds to dry any solids. And then recovery and reuse, you could recover nutrients and nitrogen, phosphorus, and potassium in the form of solids and liquids, which could be later used as a fertilizer. The second system that we looked at really just upgrades where you see the stars. And so we're adding in a different type of treatment system called an anaerobic reactor. And this essentially just allows us to recover energy in the form of biogas. And then the third system is swapping out that pit latrine for a urine diverting dry toilet. which is basically just a toilet system that separates the solids and liquids, and then adding a different type of conveyance to bring both of those solids and liquids separately to the treatment plant. And this would allow us to recover more nitrogen, phosphorus, and potassium for fertilizer production. And so when thinking about the use of this package, we wanted to think about who could use it. And so we envision a decision maker using it, which would be someone that maybe is interested in selecting a new wastewater system for their community, or it could be more broad scale, like a wastewater NGO that is interested in understanding what types of systems make sense for different types of communities. And then we also were thinking about a technology developer using it. And so this could be someone that is more on the design side of the treatment plant and is doing innovation. And so they're thinking about creating new products and trying to understand what types of communities would this work for and how to make their technology more competitive for more communities. And so first looking at the decision maker type and how they would use it. So I will present some results showing more on the selecting of the system and understanding what communities would make sense for different systems. And so I mentioned that we could vary the criteria weights, so what you value as far as each criteria. And so we varied those weights 1,000 times. And so this is just a single snapshot of one of the possible criteria weight scenarios. And so for this one, technical is weighted at 40% of the decision, resource recovery is 0, environmental is 20%, economic is 30%, and the social is 10% of the decision. And so we did this 1,000 times. So there might be one scenario where technical is 100% of the decision and none of the other factors matter. And so I'll show some line charts that kind of show how each system performs depending on what the community would value for these criteria. And so basically in the figures, if a line appears, so if this is showing a line, that means the system performed well under this scenario. But if there was no line, that would mean a different system performed well. Okay, so this is what I was talking about. So basically what you need to know here is that if there's lines, that means the system is going to win under these conditions. And so again, the order is technical, resource recovery, environmental, economic, and social. And so all you need to know for this figure is that the first alternative, the existing system, performs really well when the community really only values technical. So these lines are very high on the x-axis or the y-axis. That means those weights are high for technical. So this happens in 77 of those 1,000 scenarios. This alternative B performs really well across most scenarios. So it is selected in 922 of those community value systems. And so really it's selected in communities that value resource recovery, environmental, economic, and social performance. And then alternative C, which was the one that used the urine diverting toilets to get more fertilizer production, that system is really only selected in one scenario. So it's not a very high performing system compared to the others. And then now switching gears to think about how these systems could be improved by a technology developer. And so we were really interested in thinking about, of those 28 indicators, could you change anything to make a wastewater system improve or be selected in more communities? And so this figure is basically showing what would happen if we changed the cost of the system. So what would happen if we decrease the system, and what would happen if we increase the number of jobs for the community. And so this heat map is showing the percent of the scenarios in which alternative A is the best performing system. And so down here, this is where we started at the baseline. So about 73 of the systems, 73 of those 1,000 scenarios, it was selected. And then if we decrease costs and increase the number of jobs, we can actually increase the performance to be a viable option in 290 scenarios. So 290 weighting scenarios that would match different communities. And so this type of information is really useful for just wastewater designers, and it would help them understand what improvements they need to make it more viable for the communities, as well as maybe reduce the chance of having failures if you're actually meeting the needs in the communities. Okay, so this is my last slide. So this is just kind of a summary of everything we've talked about. So I have some links there. So if you're really interested in learning more about how to use MCDA for wastewater, you can go to our GitHub repository, which has all the code you need to do your own MCDAs. But I will say that this methodology is really applicable to a lot of sectors outside of just the wastewater and water industry. And so this could definitely be scaled up to think about other types of community problems, or if you're really motivated, you could actually do an MCDA for a decision that you're facing in your life in the future. So with that, I would like to thank you.